So all the pressure sensors we have introduced are for measuring pressure values in the common range. So it could be high pressure or it could be a negative pressure, which means is lower than the atmospheric pressure. But if you're measuring a very low pressure, so usually we call them a vacuum pressure. So vacuum pressure, that means their value is below the atmospheric pressure, so it is a negative pressure. So sometimes the ones we have introduced may not be suitable for that, because imagining you have a very high vacuum, that means the pressure value is very low. So if you use a regular, let's say a diaphragm based pressure sensor to measure it, it could be the pressure difference is too large, so it could easily damage the diaphragm or other sensing structure. So that's why for very low vacuum pressure measurement, we may need to develop some specialized pressure type. So in the next few slides, I will introduce some specific types of pressure sensors for measuring vacuum, low vacuum. So first, let me answer the question why we need to measure vacuum pressures. So in our common life and in engineering practices, we both need vacuum pressure measurement. For instance, I believe all of you have had taken freeze-dried food before. So how it works is basically you have those fresh food and then you freeze it rapidly and to a very low degree, to a very low temperature. And under this temperature, you put all the food in vacuum. And because once you have vacuum, and any vapor will be easily vaporized. So will be easily any water, either is ice or liquid, can be easily vaporized. So that means most over 98% of the moisture will be finally evaporated. So you can generate, you can do this process very quickly, and after you freeze dry those food, so their flavor and the ingredients inside all can be always easily restored once you put water back to the food. So that's why once the water is replaced, they can keep their original fresh flavor and texture and etc. So that's the principle. But you can see once we manufacture those freeze-dried food, we need a vacuum chamber. So we need to control the vacuum pressure. Of course, we need a vacuum pressure sensor. And this is our common life example. And if you look at the industry example and look at this photo, I think I used one slide before to introduce those MEMS-based sensors or devices. So a lot of manufacturing process for integrated circuit or MEMS chips. So both of them are made from silicon, and you need to use vacuum chamber. So this is a e-beam evaporator. So for MEMS micro fabrication, so you can deposit thin film metals to silicon using this machine. We call them e-beam evaporator. So in most cases, when you deposit a material, and you need to have a very clean environment. So this is the vacuum chamber is the one. And of course, if you look at the control box here, this is the very big control box for this machine, and there are several readings about the internal pressure of the chamber. And also another example in engineering practice is when we have those simulators for the outer space environment. You can see this is a very big chamber, and the people vacuum may pump out all the air inside the chamber to mimic the outer space environment. So you can see it also requires to measure the vacuum pressure. Okay, so let's look at some common values of the vacuum pressures. So we know atmospheric pressure is 101.3 kilopascal, or is 760 millimeter mercury height. column. So, and we define 1 millimeter mercury, the pressure of this value, using a new unit. We call them torr. So 1 torr is basically equal to 1 millimeter mercury. So the unit torr is commonly used to indicate the pressure, vacuum pressure values. So for different vacuum pressures, we can divide them into a few ranges. So we have low vacuum, which is from the atmosphere pressure to 25 torr, and we have a medium vacuum range is from 25 torr to 1 millitorr, and we have the high vacuum range is from 1 millitorr to 1 nanotorr. So you can see torr is just a unit to describe the vacuum pressure. And the outer space pressure, vacuum pressure, is from 1 microtorr to 3 times 10 to minus 17. So you can see, so 1 microtorr is already very low. And for different ranges of the vacuum pressures, we can use different pressure sensors. So for the low vacuum and the medium vacuum, so which is usually larger than 1 millitorr, we can still use those common pressure sensors like manometers, Berlin gauges, and diaphragm sensors to measure the pressure value. But once you go to a very high vacuum environment, so we need some specialized transducers or pressure sensors. So the first vacuum pressure measurement device or vacuum pressure sensor is called a McLeod gauge. And this schematic shows the structure of a McLeod gauge and the operation of the gauge. So you can see the gauge is designed into a tube shape, and in the tube we have a fluid. So usually this fluid is mercury. And on the left hand side, the tube is connected to the tube has an inlet, and this inlet will be connected to the vacuum source which we want to measure. And also it has a fixed volume chamber, and this tube is connected to the chamber. And at the end of the chamber, we have a capillary here, and besides it, it also has another capillary. So those two capillaries are the locations we read the pressure. On the right tube, it has a plunge, and the plunge can be manually operated to adjust the level of the fluid here. So the operation of a McLeod gauge is the following. So initially, we pull the plunge so that we can adjust this interface level to below this inlet. So after that, we can connect our vacuum source to the inlet. So you can imagine this source will pump out most of the airs inside here. So the air will be pumped out, and finally the pressure inside will reach the same pressure as the P vacuum. So that's P vacuum. Okay, so let me remove those marks. And once we reach a low vacuum state in this chamber, and what we do is we push this flange downward so that the liquid will be pushed upward, and the liquid will finally reach the chamber. So that means we will seal a fixed volume of the low vacuum or low pressure gas in this chamber. So the total volume of the gas we can seal is approximately equal to the volume of this chamber, because the tube volume is very slow. So we just regard the total volume to be this chamber volume. And once you push the plunge downward to the most, so you will reach an equilibrium state. So where the fluid level is already reached the small capillary inside here. And also because the fluid will also be pushed upward along this tube, so we will have another level, fluid level here. So those two interfaces give us two height readings. So you can read the height H1 and H2 here. So the difference of H2 minus H1, this is the final readout. So the relationship of this readout with the Mayrand, which is the vacuum pressure, is the following. So the pressure is just linearly proportional to the square of H2 minus H1. So of course, this is the sensitivity of the device. So now let's look at how we get this formula. So I will derive the relationship between the P vacuum and this height difference. So let me keep this schematic to the top right, and then I will write the equations and I will write the derivations on the left hand side. So let's look at the final volume here. So the final volume, let me use the black one, and the final volume of the gas compressed. So if we assume this tube, the cross-section area, so this tube is basically the tube here. So the cross-section area of the tube is A. So the final volume, we call the F is final. So the final volume of the gas is basically the cross-section area times the height here. And we know this height is H2 minus H1. So that's why it's H2 minus H1. And this is the final gas volume. And the final pressure in this tube, so the final pressure in this tube, we call them PF. So this guy is actually, if you look at here, so this is my P vacuum. If I express P vacuum, so I say the unit of P vacuum is millimeter mercury, so that's a pressure unit. And we say the unit of H2 minus H1 is also millimeter. So we can actually express the P final here, which is the final pressure, P final equal to P vacuum is the pressure at this level, and the pressure inside this is P vacuum plus this height, right? So it's P vacuum plus H2 minus H1. And also based on the ideal gas law, we know once we change the volume of ideal gas, so the final pressure PF times the final volume of the gas divided by the final temperature of the gas will be equal to the initial pressure here times the initial volume divided by the initial temperature. And because we know if we assume the temperature doesn't change, so just make PF equal to P initial. So we have PF VF equal to PI VI. So PF will be equal to PI VI divided by VF. So for the initial pressure, it's just the pressure at this state inside the chamber. So we know it's just equal to the pressure of P vacuum. So Pi is equal to P vacuum. And the initial volume here is just equal to the volume of the gas when the liquid interface reach this stage, so that it seals this inlet. So in this case, the volume is just roughly equal to V. So that's why Vi is just equal to V. So because the nodes still use Vi in the whole derivation, but just note V equal to Vi. So the initial volume is just the volume of this chamber. So let's keep Vi in the equation. So Pf will be just equal to P vacuum times Vi divided by Vf. And if we name this equation to be 1 and then this equation to be 2, so we can actually combine 1 and 2, and we got the following, because Pf is equal to this and P5 is also equal to this. So that's why if we just make the two right parts to be equal, will be P vacuum plus H2 minus H1 equal to P vacuum Vi and Vf. So what is Vf? So you can see Vf here is just equal to this A times H2 minus H1. So we can further write this formula equation is P vacuum Vi and then is A H2 minus H1, right? Okay, so we're almost there. So let me rewrite this part equal to this part in the next page. So this is what we have derived so far. So if we move P vacuum to the right hand side, and what we get is H2 minus H1 equal to, so I have a common factor P vacuum for the two atoms, so I factor out P vacuum, and then it will be equal to Vi A H2 minus H1 minus 1, right? So if we combine those two together, and the right part becomes P vacuum. Okay, so we are trying to combine those two parts together. So this becomes H2 minus H1, and then so it's minus A times H2 minus H1, right? And because this, from the previous slides, we know this one equal to Vf. So we can rewrite this part is P vacuum and then Vi minus Vf A H2 minus H1. So H2 minus H1 equal to this guy, and then we express Vi minus Vf. So that is equal to, so sorry, we should not do that. So what we need to do is we should express P vacuum as a function of the rest. So this will be equal to, we divide this part to the left hand side. So what we get is A H2 minus H1, sorry, just H1 square divided by Vi minus Vf. Okay, so we are there. So after we have this equation, we know, because Vf is the final volume and Vi is the initial volume of the gas. Because once we push the plunge, if you go back to look at the schematic of the McLeod gauge, once we push the flange, we are actually compressing the air significantly. So that's why the final volume here So Vf, the final volume, will be much smaller than the initial volume of the gas. So for this condition, we can safely ignore Vf here because it's very small. So that gives us the final formula is P vacuum. So this is the pressure source, right? We want to measure. It's just equal to A divided by Vi here. So note Vi is the initial volume of the gas, which is equal to the volume of the chamber. So that's the chamber volume. And then times H2 minus H1. So this is the formula we see initially. So you can see this is the readout and this is the voltage, this is the vacuum pressure. So this is the readout, is the output of the sensor, right? And this is the input. So for the same input, if we want to increase the output, so that means let's rewrite the output. So H2 minus H1. Let's just keep the square here. So just make it simple. This will be equal to divide this to the right left. So we know is P vacuum. And then is Vi divided by A. So that's why for the same input, if we want to increase the output of the sensor, so you need to increase this factor, right? So that means because this one reflects, so it reflects the sensitivity of the sensor. So that means if you want to increase the sensitivity, what you need to do is you need to increase the initial volume of the gas. So that means you need to increase the volume of the chamber. And also you want to decrease the area, which is the A here. That's the area of the capillary. So if we go back, so that's the area of the capillary here. Oh, sorry, before we use A here. So we use a lowercase a. So that's the area of the capillary. But later on, we use a capital A. So sorry about that. But this one is basically the same A here. That's the area of the capillary. Okay, so this is about the McLeod gauge. So we derived the formula, and I don't expect you to grasp the derivation of this. But if I give you this formula here, I ask you, so which parameter indicate the resistivity? Indicates the sensitivity of the device. So this is the factor actually, because this is your output, this is your input. So this factor indicates the sensitivity. I may ask you how to increase the sensitivity of a McLeod gauge. So this is the answer. You need to increase the volume of the chamber. You need to decrease the cross-section area of the capillary. And the second type of vacuum pressure sensor we'll introduce is called thermoconductivity vacuum sensor. So this sensor is actually very interesting. So it's something related to the Wheatstone bridge circuit and or the strain gauge we have learned previously. Because look at the structure of the sensor. So you have a chamber here. This is the chamber, vacuum chamber, and it has an inlet. And this inlet is connected to the vacuum source. And inside, you have a conductive filament. So this conductive filament can be connected to a power source. So it will have a current going through it. So you know, once it has a current, it will generate heat because the power dissipation. So it will be heated up, and there will be heat transfer, convective heat transfer from the filament to the chamber wall, right? And also we know due to the density difference. So if you have gas inside, and the density of the gas will affect this convective heat transfer. So the lower the density, in other words, the lower the pressure, the vacuum pressure, and it will be less effective to do this convective thermal transfer, heat transfer, or thermal conduction. So that's why once you have less effective heat transfer, and the final temperature on the filament will be higher, that means the filament will be hotter. And also we know the conductivity of a conductor, it is depending on the temperature. That means the temperature of the filament will finally affect the resistance of this conductor or this filament. So you can see the vacuum level in the chamber will finally affect the resistance readout. So once you have a change in resistance due to the vacuum pressure change, so you can measure resistance, use a Wheatstone-Bridge circuit, right? So that's why this is the circuit. You can see here we have an active chamber which we use to measure vacuum pressure here, and also we have a reference chamber here. So this reference chamber, you see the chamber is enclosed totally. There is no inlet. So we use this reference chamber to compensate the temperature effect. So that's why this is the reference chamber. We can compensate the temperature effect. So once you have this Wheatstone-Bridge circuit, and you can actually measure the resistance change here, and then correlate this resistance change to the vacuum level of the chamber inside. So to clarify again about this reference chamber, so it is used to compensate the temperature difference of the ambient environment. So the ambient temperature, to compensate this, because you can imagine if you have a higher room temperature, so that means the wall temperature will be affected by the room temperature. So you want, and once you have a different wall temperature, so the convection will be different. So that's why this one is used to compensate the ambient temperature, to make sure this Wheatstone-Bridge circuit, the two resistance values are matched. So that's the second vacuum pressure sensor, and the third one is called ionization vacuum gauge. So for the thermal conductivity vacuum sensor, is usually used to measure vacuum level down to millitorr level, so 10 to minus 3 torr. So this is a typical measurement range. But if you have even lower vacuum pressure, so we have to use this ionization vacuum gauge. So this sensor is popularly used in many high-end vacuum chamber instrument. So because it can measure vacuum pressure down to 10 to minus 7 or even lower. So it's for high vacuum pressure measurement. So this is the schematic of our ionization vacuum gauge. So the working principle is the following. So you can see in here we have a cathode, and the cathode is heated up through electric current. So once you heat it up a cathode, it's actually there will be free electrons generated. And also you have a grid here, and between the grid and the cathode we have a electrical voltage applied. So those free electrons will be finally accelerated, moving towards the grid. And once the free electrons move through the chamber here, so if there is a gas inside, and the gas will be finally ionized by the free electrons. So you will have gas ions inside the vacuum. And these ions will be also accelerated by this electric pressure, by this electric voltage. So the ions will also form a movement. So finally, if you count the total current induced by the movement of this free electron and those are gas ions. So we can actually measure the grid current. So that's the grid current we can measure. Because this current is a result of this ion gas flow and the free electron flow. So if we have a higher density of the gas, we will have more ionized gas molecules, and then we will have a higher current. So by measuring this current value, we will be able to correlate or calculate the gas density, therefore the vacuum pressure here applied. So this is the vacuum chamber, and this vacuum chamber is connected to the vacuum source through this inlet, and the cathode is inside. You have a gradient here, and then those gas ions give you the current. So that's the sensing principle of this ionization sensor. So this ionization sensor type is mainly used to measure high vacuum pressures. Okay, so in this section we talk about fluidic flow measurement. So in many engineering systems, actually we need to measure the fluidic flow when we have a fluidic system. For instance, for automobile engine, we need to measure the fluidic flow rate of the gasoline going into the engine chamber. And for designing aircraft, so we care about is aerodynamics. So in order to characterize those aerodynamics of the designed aircraft body, we also need to measure the fluidic flow rate on the body surface of the aircraft you design. So for an engineer to design a piping system going into a house, we might want to measure the flow rate of the supply of water or the natural gas to the house. So in this section, in order to measure the fluid flow rates, we need to utilize the basic principles of the fluid mechanics, and we will be able to quantify the fluid flows in two types of configured quantities, which is the mass flow rate or the volume flow rate. So we use m dot to represent the mass flow rate, and v dot to represent the volume flow rate. So those two physical quantities has actually the following relationship, because we know mass is just equal to the volume times the density. So we have m dot equal to the density times v dot. So this is the density of the fluid. The volume flow rate is usually used to quantify incompressible fluid. So for incompressible fluid, it just means it doesn't change its density in the whole fluidic system. And this is usually liquids we deal with in the fluid system. For compressible fluids, because they may be compressed, so that means their density may increase or decrease in the system. So in that case, mass is a better quantity to quantify the rate. So we use mass flow rate. So mass flow rate is for incompressible, describe incompressible fluid. So mass flow rate is to describe compressible fluid. That means the density will change, so it's better to use a mass. So it's compressible fluid. Now let's look at a general case where we have a fluid flowing in a pipe. At a specific cross section, we can quantify the fluid velocity using a vector. So we use those arrows to quantify the fluid velocity, and a longer arrow indicates a longer fluid velocity at a certain point here, and we will have a fluid velocity profile on the cross-section. We use U to represent the fluid velocity, and this U has a certain distribution over the cross-section area, so we use A to represent the cross-section area. So UA is the velocity distribution on this interface A. And the volume flow rate on the cross-section A can be calculated by taking the integration of the velocity profile on the cross-section area. So V dot, which is the volume flow rate, will be equal to the integration of the fluid velocity mu a UA, take the duration on the cross-section area. And for most of the fluids flowing through a pipe, because we know the pipe wall will actually have dragging forces on the wall, so usually the fluid velocity close to the walls will be lower than the fluid velocity in the center. So usually we have a non-uniform velocity profile, but this is not very convenient for us because for most cases we care about the fluid velocity on a specific cross-section area. So we can actually define an average fluid velocity or average velocity over the cross-section area. So we use the symbol mu included by an angle bracket. So this is the average velocity on the cross-section area, and if we use this average velocity times the cross-section area, and then this will be also equal to the volume flow rate. So now we got a very commonly used relationship or a formula we will use in this section, which is the volume velocity. The volume flow rate is equal to the average velocity on a specific cross-section area times the area of that section. So this formula is required, so please memorize it, and you may need to use it in the final exam. So by defining this average fluid velocity on this cross-section area, so we assume the velocity at different points on the area will be equal. So the equivalent schematic of the fluid flowing into the duct will be the following. So this is still the cross-section area A. So all the velocities on the cross-section area will be equal. So this is our average velocity. So those two schematic are more or less equivalent because that represent this equal sign. And if you look at the two different cross-section areas, the two cross-sections in the piping system, let's say this is A1 and A2, and if the fluid is flowing into A1 and then flow out of A2, so if we assume there is no loss of the mass of the fluid flow, which means there is no accumulation of the fluid in any locations of the pipe, so we can safely say that the mass is conserved in the piping system. In other words, the mass flowing into this cross-section area, into this cross-section, so here into this cross-section will be just equal to the mass flowing out of the cross-section. And also, if we divide the mass by time, so the mass flow rate at A1, so if m dot 1 will be equal to m dot 2. So this mass conservation law is also another basic formula you need to know or need to memorize in this section. Now let's look at a pipe with changing cross-section areas. And we focus on two cross-sections. So A1 is larger than A2. And based on the mass conservation law, so if there is no mass loss and the mass flowing into A1, so M1 will be equal to mass rate or mass flow rate flowing out of A2. And the mass flow rate M1 dot, we know mass flow rate is equal to the density times the volume flow rate. And also we know the volume flow rate could be equal to the average flow velocity on the cross-section area times the area. So we further write this for equation is rho times V dot is equal to mu1 times A1. So similarly, M2 dot will be just equal to rho mu1 U1 U2 A2. So because we don't know the property of this fluid flowing through the pipe, so it could be a compressible fluid or an incompressible fluid. So for general case, so we note the density, the two density values at the two cross-section areas to be different. So we write rho 1 here, and then we write rho 2 here. So finally we'll get, because M1 dot equal to M2 dot, so we can write rho 1, U1 A1 equal to rho 2 U2 A2. For incompressible fluid, we know the two density values will be the same because it's not compressible. So rho 1 will be equal to rho 2. And then we have mu1 times A1 equal to U2 times A2. And most of the liquids are actually incompressible, and usually the compressible liquid fluid is usually gases. So incompressible is usually liquid. And the compressible fluids are usually gases. Okay, so now let's look at one of the most important formulas or laws in the fluid mechanics, which is the Bernoulli equation. So I assume you have learned that, for a mechanics student, I assume you have learned that in the course Introduction to Mechanical Engineering. So Bernoulli equation is actually defined for incompressible fluid. And it assumes that there is no energy losses in the piping system. And with this assumption, so the Bernoulli equation will actually describe the fluid behavior in a pipe. And if we look at a specific streamline in the pipe, we'll assume along the streamline the gravity is constant. So for any points along this specific streamline, so a certain physical quantity is equal to constant. And the Bernoulli equation writes, and this equation is actually defined, specified for any points along a specific streamline. So U here is the fluid velocity at that point, and P here is the pressure at that point, and rho is the fluid density at that point, and G is the gravitational acceleration. Z is actually the elevation of the point with respect to a reference point or plane. So the sum on the left is equal to a constant value. So because this is for any point, so that means, so this sum for 1.1 in a streamline will be equal to another sum for 0.2 along the same streamline. So and the Bernoulli equation can be rewrite for 2 points along the same streamline. So it is for 2 points along the same streamline. So and if we deal with incompressible fluid, so we know the density will not change. So in this Bernoulli equation, so rho 1 will be equal to rho 2. So we can actually further generalize this Bernoulli equation and define it for 2 cross-section areas along the duct. Plus, let's say we look at those 2 cross-section areas, so A1 and A2. So the Bernoulli equation is also valid for these 2 cross-section areas, because now we are looking at a whole cross-section, and we cannot use the point fluid velocity anymore. So we have to use the average velocity. And the equation for the 2 cross-sections will write and similarly, if we deal with incompressible fluid, and rho 1 will be equal to rho 2. Now let's take a second look at this Bernoulli equation defined for the 2 cross-sections in this duct or this pipe. So because we know the mass flow rate will be conserved at those 2 cross-sections, so we know the mass flow rate is equal, and we can write, so let's just use the volume flow rate expression. So rho 1 times the average velocity at A1 times A1. So this is the first mass flow rate equal to rho 2 and U2 A2. Assuming we deal with incompressible liquid fluid, rho 1 will be equal to rho 2. So we have U1 A1 equal to U2 A2. And also from this schematic we know A1 is actually larger than A2. So because of this equation, we know that U1 will be smaller than U2, right? And if we go back to look at this Bernoulli equation, so we already know U1 is smaller than U2. So this quantity is smaller than this one. And if we assume the elevation here doesn't change significantly, so we assume Z1 equal to Z2. So they are roughly at the same level. And because U1 here is smaller than U2, is smaller than U2, so we know finally P1 here will be larger than P2, right? Because the left-hand side and the right-hand side are equal. So from this formula, we know that P1 will be larger than P2. So that means the pressure here in this schematic, the pressure on A1 will be larger than pressure on A2. And if we can quantify the pressure difference at the 2 cross-section areas, or 2 cross-sections, so P1 and P2, so if we can quantify the difference, let's say P1 minus P2, we can actually use the Bernoulli equation to calculate the average fluid velocity on one of the 2 cross-section areas. So we can use the Bernoulli equation to calculate U1 or U2. So this is based on the Bernoulli equation. So this is one of the sensing principles we will introduce to measure the volume flow rate of a specific fluid system using Bernoulli equation. So this type of fluid sensor, fluid meter, we call them differential pressure fluid meter. We call them differential ones. So it's pressure differential flow meters. So we call them differential pressure flow meters. So differential pressure flow meters. So we will introduce the details of those flow meter design in a later slide. Okay, so far we have introduced the basic formulas or laws of in fluid mechanics we will use in this fluid sensor measurement, in the fluid measurement section. So from now we will introduce a few types of flow meters based on those principles. So please go to the page 2 of the PPP slide. So the first flow meter we'll look at is called rod meter. And the structure of the rod meter is very simple. So you have a tube with a varying cross-section area. So you can see the cross-section area is changing with its height, with the height of the position. And inside the tube we have a float. And the shape of float could be a spherical shape. It could be also a cylindrical shape. And the fluid flow is going into the pipe from the bottom inlet. And you can imagine if you have once you have a fluid flow passing through the float, and there will be a dragging force applied to the float, so it will finally lift the float to a certain height, until the gravitational force and the floating force reach the balance. So that means for a certain flow rate, you will have a certain height here. So finally we can actually measure the height reading, and we can read the height so that we can measure the volume flow rate. So this is the principle of the rod meter. Because in the rod meter, the cross-section area is changing, so we also call the rod meter as a variable. It's called variable area flow meter. So it's a variable area flow meter. So we will do an analysis of the working principle of this rod meter, and it will show you actually the relationship between the height measurement of the float and the volume flow rate. So let's look at the force balance on the float when it reaches equilibrium, and there will be three forces applied to the float. So the first force is the gravitational force of the float, so we name it Fg, and then the second force is the buoyant force applied by the fluid to the float. The third force is the dragging force because the fluid flow and applied to the float. So the three forces reach the balance, so we have Fb plus Fd equal to Fg. The buoyant force is equal to rho F, which is the fluid density, times the volume of the float times g, which is the gravitational acceleration. So rho F here is the fluid density. And the gravitational force is equal to the density of the float. So here we use rho b to represent it. So it's the density of float. So b represents buoyancy, and times the volume of float times g. And the drag force is given by 1/2 times a constant is the drag coefficient times the fluidic density times the area, which is called front area of the float, and then times a velocity square value. So A is called the front area of the float. And the CD is the drag, is a constant, we call them drag coefficient. And the VA, we call it annular velocity. So let me replot the schematic of the pipe, and then I will give you the two definitions of the front area and the front area of the float and the annular velocity. So the front area is defined as the float projection area on a front plane across the fluid flow direction. So if you project this float along this direction to a front plane, and we can take the projection, so you have a projected area. So this is called the front area. For the angular velocity, so we need to sketch on this schematic as the following. So we plot out the plane going through the center of the float here. So you can see the flow will actually only go through these band areas, right? So if you look at the top view, because this is a side view, so if you look at the top view, so this area will be represented to be, so this represents the blocked area by the float, and then this is the outer circular area, so which correspond to this circle. So basically this area, if you take, so that is called annular. So this is called annular area. And then the velocity, the fluid velocity, which is the average fluid velocity going through this annular area, we call them annular velocity. So if we plot it out here, so if you take this average velocity, and that is called annular velocity. It's just the velocity going through this annular area where it really does allow the flow going through. So that's what we call the annular area. So we have got all the expressions of the three forces. So let's put those expressions and fit these expressions into this force balance equation. And if we rewrite this equation and we move this atom to the right, so we will have the following. And then we express VA as a function of the rest quantities, so we can get the VA expression. And so for most of the load meters, it will be used to deal with gas flow, volume flow rate measurement. So for gas, its density, the fluid density rho F, is much smaller than the float density rho B, right? So this atom can actually be safely cancelled because it's much slower compared to rho B. So it's for gas. And VB will be approximately equal to 2VG rho B CD A rho F. And for the rho meter, so the rho F value, which is the fluid density, will remain constant as the annular area. So where is the area, the flow path through the float? And so rho f will remain constant. And also let's look at the rest of the quantities here. So CD is the dragging coefficient. So it mainly depends on the shape of the float. So for the certain float with a specific shape, so once the float moves vertically along the duct of the voltmeter, so this dragging coefficient doesn't really change at all. So CD is also a constant. And volume is the constant, volume of the float is constant, gravitational acceleration is constant, and rho b is the float density is constant. So you can see actually, and also, and A here, sorry. So A here is the front area of the float along the fluid flow direction. So A is also a constant for a chosen shape of the float. So A is also a constant. You can see all the physical quantities in this expression is actually constant. So finally we can draw the conclusion: the annular velocity in the voltmeter is constant. So we can draw this conclusion: VA is constant. And if we take a second look to the annular area and the fluid flow going through it. So the annular velocity VA is a constant, and the volume flow rate across the annular velocity is just equal to, let's say, the volume flow rate on the annular area will be equal to the annular velocity VA times the annular area AA. So that's the annular area. So please note that the A here is different from AA. So they are different quantities. So A here is the front area, and AA here is actually the annular velocity, annular area. So if you look at top down, giving you the top view, so this is the annular band. So we're talking about this area. So that's AA. So it's the annular velocity, annular area. So you can see now the volume flow rate passing through the voltmeter is actually linearly proportional to the annular area, because we know this annular velocity is a constant. So now the design of the voltmeter becomes more straightforward, because you can imagine if you design the shape of the pipe here so that this annular area, we give the name AA, is linearly proportional to the vertical position of this annular plane. So you can see if you give a scale on the vertical direction, so if AA is linear proportional to the vertical position, we can actually correlate this vertical position, which is our readout of the voltmeter, with the volume flow rate. So they have a linear relationship. But now the condition or the requirement of the voltmeter design is actually you need to design the profile of this pipe to make AA to be linear proportional to the height difference. So let's give a position. Let's give it the h. So h corresponds to the height. So we want this to be guaranteed. So we need to design the profile of the duct sidewall. So we need to design the duct profile. So the final output will be the duct profile is designed in such a fashion that this annular area here is linearly proportional to the height information. So that is the principle of the rotmeter, because now we can quantify or we can measure the volume flow rate by looking at the vertical position of the float once we have a fluid flow passing through the rotmeter. So let me summarize the requirement for the rotmeter principle, because I given you this derivation, but some of the formulas you're not very familiar with, because for instance the driving force formula. So I will not require you to grasp the derivation, but I hope my requirement here is I hope you can understand the working principle of the rotmeter. So there are a few points you need to know. The first one is the working principle of the rotmeter is basically we are measuring the volume flow rate by looking at the height of the float along the vertical position. And the second point is, although I didn't require you to grasp the derivation, but you need to know that after we derived this, we found out the annular velocity in the rotmeter it remains constant. So it doesn't depend on the vertical position. So in any vertical position of the float, so the annular velocity is always a constant. And the third point is that once we know the annular velocity is constant, and we also know the volume flow rate is equal to the annular velocity times the annular area. So in order to correlate to give a linear relationship between the volume velocity, volume flow rate, and the height, so we need to define the profile of the duct so that we can have a linear relationship between the annular area and the height, the position, the vertical position or the height of the float. Okay, so that's all about the Thursday's online video lecture, and I will post it on YouTube and send you the links.